Alright, so my name is Shiheem Jones, and I also work with Dr. Brian immensely at the Nevis Laboratory, and I also helped develop the new edge sensor for the mirrors of the CTA. So before I start, this is my introduction. And before I start talking about CTA, I want to explain one of the telescopes Zachary introduced, Veritas. This is the one that we currently use the most for gamma ray detection. And what Veritas stands for is Very Energetic Radiation Imaging Telescope Array System. And as stated, we use it to detect high-energy gamma rays. And we do this by our Earth's outermost atmosphere protects us from these gamma rays by breaking them down into electron and positron pairs. And they continue to break as they fall down to Earth. And by picking up these electrons and positrons, we can determine the energy and the direction the gamma rays came from. And it does this by using 4 12-meter optic reflectors on one single mirror. And the project that's being developed now is the Cherenkov telescope array. And what this does is, instead of detecting the electron and positron pair created by the gamma rays, it detects the congenital of light that reflects off of them as they fall down to Earth. And it does this by picking it up into the primary mirror and then reflecting it back into a secondary mirror, which reflects back into a camera. And what this does is it gives us a higher resolution so we can better determine the energy of the gamma ray, and the material used for it is also cheaper. And this telescope is currently under development by thousands of scientists all over the world. And one of the sciences that we hope to test by using gamma rays is the Lorentz invariance violation. What this basically is it takes into question the theory of relativity, which is, for example, if you're an observer and you have two objects moving towards each other at 1 meter per hour, the observer will see both the objects moving at 1 meter per hour, but each object will see each other moving at 2 meters per hour towards the same direction. Is that confusing?
Yes, it is.
You should use the bus analogy.
Okay. Maybe I should use object. Let's say me and Annette are moving towards each other at 1 meter per hour. You all see this at 1 meter per hour, but I see myself moving towards her at 2 meters per hour, and she sees me moving towards her at 2 meters per hour. Understand?
Yeah.
And what the violation is we see that the speed of light doesn't adhere to these rules, because as we know so far, the speed of light is the highest median of speed. So going back to our example, if we were both moving at 3/4 the speed of light, we would still see each other moving at the speed of light. And this violation proves that nothing goes faster than the speed of light. So this is the mirrors of the CTA, and as I stated before, this is the primary mirror, and they're made up of very small mirrors connected to each other, and the light will hit here and then reflect that into this smaller mirror, which is also made of small mirrors connected together, and reflect back to the camera in the center. So one thing about the CTA is the distance and position of the mirrors to each other is very important, because they're off by microns of distance. It could mess up the whole measurement. So to prevent this, we created edge sensors. And what they are is we use a combination of laser and webcam technology to determine the location of each small mirror adjacent to the mirror that's next to it. So we can make sure that they're all aligned to each other. And as stated, this is important to CTA because these small measurements really matter. And we need to do tests before we can develop these edge sensors. And one of the tests we did was using these materials. This is the motion sensor that we use to move the opal diffuser and the camera around by small microns of distance. It's very precise movement. We use the opal diffuser right here to display the laser. We use the pinhole to stop the diffraction of the laser. so we can have it more colonized and precise on the opal diffuser. And we also use this stage for all of the materials. So the method that I did for my experiment is that I created a 1 millimeter cross, which is an X formation, using the Y and X axis of the opal diffuser. And I took 300 pictures of the points 1 millimeter apart from each other, starting from 4.5 to negative 4.5 on the X axis, and 2.5 to negative 2.5 on the Y axis. And by using software coding programs used by many physicists, which is called root, we were able to determine the centroid of each of these points, and then in retrospect determine the average centroid of all the centroids. And we recorded each of these centroids so we compared them to each other. So, our hypothesis was the results we expected to see were the centroid means of the pictures taken of multiple locations of the laser points are going to be 50 or close to 50 pixels away from each other, because that's about the distance of 1 millimeter apart. And in addition, we expected to see all these points would show a best fit line or average curve of 50 pixels going forward. So, these are my measurements, and as you can see, our hypothesis was disproven because the points headed towards the center seem to follow this curve. However, some of the points that are closer to the edge don't. And there's a reason for this. So as stated, our first results was our hypothesis was incorrect for the first test we took. And our points didn't match up to the best fit line we created. And we found out that the problem is where there are some problems with the software we use and the motion control sensitivity. The motion control sensitivity is when you using this specific motion controller, if you go past the point and then you try to move forward, then kind of move it back and forth, it changes the position of the micron slightly, which affects the measurements. So we took another test without doing this and heading in one direction, and we saw better results, but it wasn't anything significant. And this is the problem with software. So these pictures are not taken as good, by the way. But as Zachary stated, by using the software, it creates a box around the point, which eliminates all the background noise, so we can get a better understanding of the micron. However, this program makes the same size box no matter where the point is located. So in the center, this works fine because the box can cover the whole point. But headed towards the edges, the box doesn't cover the whole point, which means it doesn't cover up all the background noise. So in this example right here, as you can determine that the centroid is probably around this point right here, because it's so close to the edge and the program didn't accurately determine the centroid, it believes the centroid is around this area, which gave us incorrect results. So, our future plans is to complete more measurements with different distances between the points, so we can test different variables to make sure that we can determine the distance between the mirrors at any change. And we're going to change various variables of the test, such as the pinhole size and the intensity of the laser. We're going to improve upon the abilities of the software to hopefully develop a software where the box would cover it at all edges of the opal diffuser. And finally, our main goal is to mass produce this product and attach it to all the mirrors so we can just start developing the CTAs. And these are my references. And these are my acknowledgements. I want to give thanks to my mentor, Dr. Brian Mensky. I want to give thanks to assistant, Ganesh, and she supplied us with various readings so we can get up to speed with Veritas and CTA and gamma rays. I want to thank Danny Nazo and Alice Rose. They were originally working on this project before us, and they helped teach us how to take these measurements and apply it to the CTA, and also taught us about the fraction. I want to thank the staff at the Nevis Laboratories for helping us with any problems that we came across when doing the readings and the research. And I want to thank the Harlem Children's Society along with Dr. Stat and all of you in the audience.
No. I think you can talk about the lenses.
Lenses and their evaluation.
Yeah.
And that was there are many different sciences to Veritas and Fermi. Fermi being the space satellite. And, you know, these telescopes hope to aim to discover the answers to all these sciences. But it's up for debate which sciences are most important to focus on.
So, how this telescope to study Lorenz's invariation?
One more time?
So, how this telescope to study the Lorenz's?
How does it solve it?
How to study it?
Oh, how does it study it? Okay, so it studies it by, you see, as I stated before, nothing goes faster than the speed of light. Well, gamma rays come pretty close to going at that speed, so they're the perfect subjects to study the test to see if this violation is really true or not. That is your question. Anyone else? Yeah.
How can you measure the speed of light? You said that if two things are going at speed of light across each other, what they see is the same as what we see, speed of light. So how can you measure that? There's no way of measuring it, is there?
I think it.
I can answer that for you. It's based on vacuum. Like what they did was they did an experiment. They actually closed up a vacuum space where nothing could get in. So they measured the speed of light using a space literally nothing could get in. So it wasn't like they just went outside and measured it, but they had it in a control area. That's how they see the speed of light.
And as for the example,
It's a temperature, by the way. Sorry.
Oh, I'm sorry. As for the example, I think that. All right, let me re-explain it. When I was saying that if we're moving at 3/4 the speed of light, according to the theory of relativity, we should see each other moving at 1.5 the speed of light. However, the violation states that that's not the case. We will still see each other moving a little bit less than the speed of light. I think you had a question?
Yeah, I have a question. So once you use the technology to detect which direction the gamma waves are coming from, like, what do you expect to gain from it? You know, and how would that help humanity?
So by detecting the direction of the gamma rays, we can hopefully find out the source. And from the research that we've done so far, there are a couple of sources that we found. We found that they come from supernova remnants. They come from active galaxy nuclei, and they come from exploded neutron stars. And the study of high energy things in space is so we can hopefully find a way to either harness it or at least have a better understanding of it.